Welcome to the deep dive today. We're diving into the world of string theory.
Oh, string theory.
You know, that wild idea that the universe is made up of tiny vibrating strings.
Yeah.
We've got a fascinating timeline history of string theory as our guide today.
Oh.
We'll trace how this mind-boggling concept evolved over decades.
Well, you might be surprised to learn that string theory actually started as an attempt to understand something completely different.
Really?
Yeah, the strong nuclear force.
The strong force,
Yeah.
the one that binds protons and neutrons together.
Exactly. It all began in the late 1960s with this physicist, Gabriele Veneziano.
Okay.
He was wrestling with this puzzle of the strong force, and he stumbled upon a mathematical formula now called the Veneziano Amplitude.
The Veneziano Amplitude.
It seemed like a pretty standard equation at first, but then
Right.
it's like he accidentally opened a secret door in the universe.
Oh, wow.
Yeah. This formula hinted at the existence of something much more fundamental. These tiny one-dimensional vibrating strings.
Wait, hold on. So he was trying to understand the strong force, and he ended up finding clues about the building blocks of reality.
It's pretty wild, right?
That's amazing.
This discovery set the stage for physicists like Leonard Susskind, Holger Beth-Nielsen, and Yoichiro Nambu.
Okay.
They came along and said, hold on a minute, what if these strings are actually the fundamental components of everything? What if, instead of picturing particles as tiny points, we imagine them as these tiny strings vibrating at different frequencies?
So that's where it starts to feel like a sci-fi movie.
Yeah.
Tiny vibrating strings making up everything we see and touch.
It's a huge shift in perspective.
It's mind-blowing.
And this idea that particles are actually tiny vibrating strings is the core concept of string theory.
Okay, so we've got these strings,
Yeah.
but where do they exist?
Well, that's where things get even more interesting.
Okay.
See, in the 1970s, as physicists were developing string theory, they encountered a few wrinkles. Yeah, like how to incorporate both fermions and bosons.
Fermions and
Yeah.
bosons.
Yeah,
Okay, for those of us who aren't theoretical physicists, could you explain what those are?
of course. So in the quantum world, there are these two fundamental types of particles, fermions and bosons.
Got it.
Fermions, like electrons and quarks, are the particles that make up matter.
Okay.
Bosons, on the other hand, carry forces, like photons, which carry the electromagnetic force.
So fermions are like the stuff, and bosons are the messengers.
That's a great way to put it.
Cool.
And early versions of string theory had trouble incorporating both of these types of particles into a single framework.
I see. So how did they solve this problem? It sounds like a pretty big hurdle.
That's where supersymmetry comes in.
Supersymmetry.
In 1971, Pierre Ramon introduced this idea of supersymmetry into string theory, and it was a game changer.
Okay, supersymmetry. What does that even mean?
Think of it as a kind of symmetry that links fermions and bosons together. It's a way of saying that for every fermion, there's a corresponding boson, and vice versa.
Okay.
This idea of supersymmetry was incredibly elegant because it helped weave both fermions and bosons into the fabric of string theory.
So supersymmetry was like this missing piece of the puzzle.
Exactly.
And then, just a few years later, in 1974, John Schwartz and Joel Shirk made a discovery that sent shockwaves through the physics community.
They were studying the different particles predicted by string theory when they stumbled upon something truly remarkable.
This is where things get really interesting, right?
Absolutely.
Okay.
They found that string theory predicted the existence of a massless particle with a spin of 2. And guess what?
What?
This particle fit the description of the graviton,
Graviton.
the hypothetical particle that carries the force of gravity.
Wait, you're saying that the string theory,
Yeah.
which initially was trying to explain the strong force inside atoms, suddenly had something to say about gravity.
Yes.
Wow. I can see why physicists were so excited.
It was a huge deal.
Yeah.
It suggested that string theory might actually be a theory of everything, capable of uniting all the fundamental forces of nature, including gravity, which had always been a bit of an outlier in the quantum world.
So we've got strings, we've got supersymmetry, and we've even got gravity entering the picture. String theory is sounding pretty impressive so far.
Yeah.
But our timeline tells us that the story takes an unexpected turn in the late 1970s.
Oh, yeah.
What happened?
Well, As with any scientific theory, string theory had to face the scrutiny of experimental data.
Right.
And in the late 1970s, a rival theory emerged that did a better job of explaining the strong force, quantum chromodynamics, or QCD for short.
So this new theory, QCD, outshone string theory when it came to explaining the experimental evidence.
That's right. This highlights a recurring theme in science. Sometimes a theory, even if it's not wrong, can be sidelined if another theory better explains the available data.
It makes you wonder what other promising ideas might be out there, right?
Yeah.
Just waiting for their moment to shine.
And for string theory, that moment would come in a truly revolutionary way in the 1980s.
Well, on the edge of my seat.
Yeah.
Let's dive into that next chapter and see how string theory makes its comeback.
Okay.
Also, string theory hits a bit of a roadblock in the late 70s with the rise of QCD. But then something happens in the 80s that completely changes the game. What was this turning point for string theory?
It was a breakthrough that reignited enthusiasm for string theory. It launched what's now known as the first superstring revolution.
First superstring revolution.
Okay, in 1984,
Yeah.
two physicists, Michael Green and John Schwartz, tackled one of the biggest challenges facing string theory at the time, inconsistencies known as anomalies.
Anomalies. Can you explain what those are and why they were such a problem for string theory?
Sure, think of anomalies as mathematical glitches that can
Yeah.
pop up in a theory, making it inconsistent
Yeah.
or even nonsensical.
Okay.
In the context of string theory, these anomalies were threatening to derail the whole idea, like cracks in the foundation of the theory.
So Green and Schwartz essentially patched up these cracks.
Yeah, that's a great analogy. They showed that in superstring theory, the specific version of string theory that incorporates supersymmetry, these anomalies miraculously canceled each other out.
So superstring theory was mathematically sound. That must have been a huge relief for string theorists.
It was a major victory, and it sent a wave of excitement through the physics community. String theory was suddenly back in the spotlight, and it was brighter than ever.
I bet. But hold on. I remember you mentioned earlier that there are actually 5 different versions of superstring theory.
Right.
How did that play out?
That's right. In the years following Green and Schwartz's breakthrough, physicists discovered not one, but 5 consistent versions of superstring theory.
5 different versions. That seems complicated.
Yeah, it did seem confusing at first. Imagine trying to solve a puzzle, and you suddenly realize there are 5 different sets of pieces that all seem to fit together in slightly different ways.
I can see how that would be a head-scratcher. So did physicists eventually find a way to unify these 5 different versions of superstring theory?
They did. But before we get to that, we need to address another big challenge that arose during this time. The problem of extra dimensions.
Ah, yes. Extra dimensions. One of the most mind-bending aspects of string theory. We're talking about dimensions beyond the familiar 3 spatial dimensions and 1 time dimension that we experience, right?
Exactly.
So if they exist, where are these extra dimensions hiding?
That's where the concept of compactification comes in.
Compactification.
Physicists propose that these extra dimensions are curled up into tiny, compact spaces, so small that we don't notice them.
It's like a tiny rolled up piece of paper. We only see the flat surface, but
Yeah.
there's a whole other dimension. Curled up tightly inside.
That's a great analogy. And to describe these curled up dimensions, string theorists turned to complex mathematical objects called Calabi-Yau manifolds.
Calabi-Yau manifold.
These manifolds have all sorts of interesting shapes and properties, and they provide a way to think about how these extra dimensions could be hidden from our perception.
So string theory is not only telling us that there might be more dimensions than we thought, but it's also giving us mathematical tools to describe them. Pretty amazing. But let's get back to those 5 different versions of superstring theory. Did physicists ever find a way to unify them?
They did. And this brings us to the 1990s, which ushered in a second superstring revolution.
2 revolutions in one theory. String theory must have been a wild ride. Tell me more about this second superstring revolution. What happened?
It all started with a physicist named Edward Witten, a true rock star in the world of theoretical physics. In 1995, Witten proposed something called M theory.
M theory. What does the M stand for?
Well, that's a good question. Witten himself has said that the M could stand for magic, mystery, or membrane, but the important thing is what M theory did for our understanding of string theory.
So what did this mysterious M theory do? How did it change the game?
M theory was Witten's brilliant solution to the puzzle of the 5 different string theories.
Okay.
He proposed that these 5 seemingly separate theories were actually different facets of a single overarching theory, M theory, which existed in 11 dimensions.
11 dimensions? Okay, now my head is really spinning. So all those 5 different string theories were just different ways of looking at the same underlying reality.
That's the idea. Imagine looking at a sculpture from different angles. Each view might look different, but it's still the same sculpture. Similarly, the 5 string theories were like different perspectives on the same 11-dimensional M theory.
That's incredible. But wait, if these theories are all connected, how does that work mathematically?
That's where another fascinating concept comes in, dualities.
Dualities.
Think of dualities as mathematical bridges that connect seemingly different physical theories.
Right.
They show that theories that appear completely distinct can actually describe the same underlying physics, just in different ways.
Okay, so it's like looking at the same object from different angles.
Exactly. It was through these dualities that physicists began to realize that the 5 string theories and M theory were all interconnected in intricate and beautiful ways.
It's like uncovering this hidden web of connections in the universe. The second revolution sounds even more mind-blowing than the first. But our deep dive isn't over yet, is it?
Not at all. The story of string theory continues, with new discoveries and challenges emerging in the 2000s and beyond.
Well, I can't wait to hear about it. Let's jump into the next chapter of this incredible scientific saga. We've journeyed through the history of string theory, from those surprising beginnings in the 60s to the revolutions of the 80s and 90s. It feels like we've covered so much ground.
Yeah.
What stands out to you as we enter the 2000s?
The landscape of string theory expanded even further in the 2000s. It's like explorers charting a new continent, discovering vast uncharted territories.
I like that analogy. What kind of uncharted territory are we talking about here?
Well, as string theorists explored the mathematical depths of the theory, they began to realize that the equations didn't have just one solution.
Oh.
There was a vast, almost incomprehensible number of possible solutions.
Hold on. Are you saying there could be multiple solutions to string theory?
That's right.
Wow.
Each solution represents a different possible universe with its own unique set of physical laws and constants.
Okay.
This realization led to a concept known as the string landscape.
The string.
This immense theoretical space encompassing all these potential universes.
Okay. I think I'm starting to see where this is going. We're talking about the multiverse, right?
Exactly.
The idea that our universe is just one of many, perhaps an infinite number of universes coexisting out there.
And while the idea of a multiverse had been around before string theory, the string landscape gave it a whole new level of theoretical grounding. It's like string theory opened a window into this vast cosmic realm of possibilities.
Yeah. It makes you wonder what those other universes might be like. Could they have different laws of physics, different dimensions? It's mind-boggling to think about.
It certainly is. And it raises some profound philosophical questions about the nature of reality and our place within this grand cosmic scheme.
So string theory, in a way, took this somewhat fringe idea of a multiverse and brought it into the realm of scientific discussion.
In a way, yes. But it's important to acknowledge that the concept of a multiverse is still highly debated within the scientific community.
Of course.
And it leads to some challenging questions. For example, if there are countless other universes out there, how do we make sense of our own universe's seemingly special conditions that allow for life to exist?
That's a great point, and it highlights one of the major challenges facing string theory. If we can't observe these other universes, how can we test the idea of a multiverse?
Yeah.
Or even the validity of string theory itself?
That's a key question and a source of ongoing discussion and debate.
Yeah.
String theory has been criticized for its lack of readily testable predictions.
So how do string theorists address this challenge?
Well, some argue that a theory's value isn't solely determined by its immediate testability. It can also lie in its ability to inspire new ways of thinking, to connect seemingly disparate ideas, and to push the boundaries of our understanding.
So even if string theory isn't experimentally verifiable right now, it still holds immense value for its ability to inspire new ideas and insights in theoretical physics.
Exactly. And who knows, perhaps future technological advancements will allow us to test some of string theory's predictions.
Yeah.
But even without direct experimental confirmation, string theory has had a profound impact on our understanding of the universe.
Can you give us an example of string theory's impact on other areas of physics?
Absolutely. String theory has led to breakthroughs in black hole physics, providing new insights into the nature of black hole entropy. a measure of the disorder or randomness within a black hole. It has also influenced cosmology, offering new perspectives on the evolution of the early universe. And perhaps most significantly, string theory has led to remarkable connections between seemingly unrelated areas of physics, like gravity and quantum field theory.
So even if we can't see strings directly, the ripple effects of string theory are felt throughout many areas of physics. It's like string theory is a hidden force, shaping our understanding of the universe.
That's a beautiful way to put it. And I think that's one of the most important takeaways from our deep dive into string theory. It's a theory that continues to challenge us, inspire us, and push the boundaries of what we thought was possible.
It's been an incredible journey through the evolution of this remarkable theory. From those humble beginnings with Veneziano's formula to the mind-boggling concepts of the string landscape and the multiverse, string theory has stretched our imaginations and deepened our appreciation for the complexities of the universe.
It's a reminder that the pursuit of knowledge is an ongoing adventure, full of surprises and unexpected turns. And even if we don't have all the answers yet, the journey itself is filled with incredible insights and a sense of awe at the mysteries of the cosmos.
Well said. So to our listener, we encourage you to keep exploring, keep questioning, and keep your mind open to the wonders of the universe. Who knows what incredible discoveries await us in the future. Thanks for joining us on this deep dive into the fascinating world of string theory.